I see a few MCM folks here. Moloco Commerce Media is the company's AI-native retail media business that enables retailers and marketplaces to build ad businesses that balance shopper experience and with advertiser performance. And so today's topic is G4, our spotlight. So just to recap, what are the main features with the G4? First of all, is GPU compute. So it has NVIDIA RTX Pro 6000 Blackwell GPUs, and then it actually has the MIG. I think some other folks already covered it. It's basically like a fractional GPUs, so that we can actually utilize GPUs much better. And then I think this is less covered in previous slides, but G4 actually has titanium supported with the hyperdisk block storage, and this is actually it benefits a lot, which I'll cover next in the next slides. But first of all, let me introduce how our ML inference workload is in Moloco. So unlike other companies who do mainly on the LLMs, we primarily work on the recommendation model. So I think we already covered like economics behind these ML inferences. For us, the two things are very critical. First one is latency. So since we do real-time bidding, sub-millisecond response times is required for the auction participation, and this is very critical. So that's one constraint. And then the other one is the throughput. So we serve 10 million QPS ML inference. So right now, like in split second, like we do like 10 million request serving. So that means we need to really, really be thoughtful about the throughput so that the cost efficiency of the serving is not impacted. So this is our main ML inference workload. And then how we try to optimize is, first of all, we offloaded the CPU part of the compute outside the GPU node. So previously in this the first before section parts, we had like 80% or to 90% of the CPU utilization, which means that it's the workload and then the compute is bottlenecked by the CPU. So we weren't able to utilize much GPU early on. So we did a few different optimizations to offload the CPU to a different part. And first one is by just upgrading from the G2 to G4, it has a titanium chip integrated in the G4. So titanium chip basically does the network I/O and then the storage I/O outside the host CPU chip. So it reduces the CPU utilizations on the host. So that's one optimization that naturally comes with just using the G4. And then what we did on our side is to have like a separate architectural shift from having a separate dedicated CPU only node, as you can see on the after part. So we have like CPU only node that we scale independently, like an NTU high CPU 80. But then we use this GPU heavy workload only on the G4 side. So this was two optimizations that we did to offload the CPU intensive task separate, like outside the G4. Okay, and then the second one is GPU partitioning. So this is about the multi-instance GPU, the MIG feature that we talked about earlier. So just to recap, MIG feature allows GPUs to be securely partitioned up to like 7 separate GPU instances for the CUDA applications. It provides multiple users with like separate GPU resources for optimal GPU utilization. So how this helps with us is to do granular scaling and like to serve multiple models. So first of all, for granular scaling, it reduces our autoscaling increment from like one whole GPU, which is really powerful. Like G4 itself is pretty powerful, but like we may not need the whole like GPU node to serve the whole like traffic. So it just reducing that to the 1/4 like quarter size slice prevents us to over provision for the low traffic models. And then the second one is multiple models. So it consolidates like multiple independent low traffic models into a single physical node instead of having like 2, 3, 4 different nodes. So as you can see on this the diagram, previously if without the MIG feature, we have to put a single model into one node. However, we can now fit in like 4 different nodes with the quarter size slice with the MIG feature. Okay, and then the next best practice is to use the lower precision. Basically, it prioritizes the we recommend to prioritize the lowest possible precision that maintains ML model performance. I think previous slides covered like there are some other lower precision compute like BFlow 16, FP8, and even FP4. We primarily utilize the BFlow 16. So even if we just look at the spec on the NVIDIA RTX Pro 6000, it has 120 teraflops for the float 32 operations, but it actually has a 1 petaflop of compute power for the BFlow 16. So it's really beneficial to have the performance gain with this. And then and then since this is using a less bytes, it actually also have a memory efficiency of just like reducing it to like 50%. So and then we saw a performance gain of like 2.14x throughput. So yeah, using the lower precision actually helps a lot with increasing the throughput. Okay, just for summary and the key takeaways. So optimize the VM shapes. So unlike the CPU nodes that could have like a flexible CPU to memory like ratios, for G2s or G4s, we need to have some kind of fixed size. So we have to offload some of the CPU part of the compute to a different node so that we can maximize the use of the GPUs. And then the second one is multi-instance GPU, the MIG feature. If we can partition the GPUs for the granular scaling, then we can serve multiple like models in a single node and have better GPU utilization. And then this is just one I didn't mention in the slides, but updating the software stack to the latest version and then have the best compute capabilities is really important because like it actually fully leverage the kernels and hardware advancements. So we definitely recommend like building your binary application that uses the latest CUDA drivers and kernels. And then the last one is leverage the lower precision. So we use the BFlow 16 inference to maximize the throughput, but there are also other lower level operations like float 8, FP8, and the FP4 that's all available in the G4. So, yeah, thank you.